back into common sense mechanics. So this is making parts when you're designing your robot, and after you've designed it, you move on to actually building it. So these are some things to keep in mind. Flat metal is, you can use it for a lot of things because it's easy to bend. You just keep in mind that it's probably not going to be the strongest depending on how you use it. When you're tapping holes, you should remember that for the same tap, you're going to want to make a bigger pilot hole in steel versus aluminum because steel is a harder material. It's basically you put threads inside a hole rather than using a nut, putting a screw through and a nut on the other end. And then file, sand, and polish. So these are just, whenever you go to a competition, rookie teams probably don't know this, but a judge comes out and in an inspection he'll check over your robot for any rough parts, sharp parts, anything that, or things that might damage the field. So do things like round your plastic corners. You can do this actually using a torch. If you lightly use a torch, it'll melt the edges of the plastic a little bit and give it a rounded look. And double drilling your channel. So I don't know how many of you got a chance to do that. This next slide shows a picture of that. And basically this is a way, what we do is we do this, we double drill every piece of channel before it ever makes it onto a robot because this gives us a lot more versatility in what we can do, a lot more places to attach parts, while at the same time the strength is almost the same. If you look up there, you can see the extra set of holes where the arrows are. If you want to learn how to actually do this, when we have another break, you can go over there, and that's where we do it. And then going back to the previous slide, our laser cutting and 3D printing, these are two really common tools and methods that FTC teams use for building their parts. The difference is laser cutting is a subtractive method, which means you're removing material. But the thing is, subtractive methods usually give a stronger end result. Rather than, so a piece of plastic that you laser cut is probably going to be stronger than a piece of plastic you 3D print. But on the other hand, you can make more complicated parts for 3D printing. So it really depends on what you want to do, how you want to use it.
Okay, so this is just a quick video on how we bend plastic. If you ever want to look at this again, it's on our Instructables website, which you can show you.
So here we're going to be bending this piece of plastic at 90 degrees, folding this way. So what I have assembled here is the plastic itself with a line drawn across where I want to bend it. I have a couple of clamps and a couple of pieces of scrap wood. The number of clamps and pieces of scrap wood you'll need changes based on what you're bending. We also have underneath a angled piece of aluminum that we have clamped in the vise. And this is what we'll be bending our knife over to make a 90-degree angle. Lastly, we have our heat gun itself. It's, ours is a pretty nice one, but any heat gun will probably do. We usually run it about 730 degrees Fahrenheit. So, let's get started. What I'm first going to do is take my piece of plastic and clamp it onto the piece of angled aluminum so that I can bend it over and achieve 90 degrees. I'll take one of my pieces of scrap wood and place it as close as you can to the top of the, as close as you can to the bend because you get a greater support. Clamp that down. So that's in there solidly. Then what we'll do is we'll take the heat gun and we'll start heating it up on high to this third dot, which makes it 730 degrees. And you run the heat gun back and forth across both the front and the back of the piece of plastic. While you're doing this, you want to have a finger up on the top of the piece of plastic or away from your bend, just pushing lightly to check and see when you think you're ready to bend. So you can see now how it's not springing back as quick. That's how I know I'm ready. So I turn off the heat gun to cooling, grab my third piece of plastic, and push the bend down with my fingers and hold that there. Then I can take my third clamp and clamp this piece of plastic down. And I'll wait about 30 seconds or until the heat gun is finished cooling. Okay, so now my plastic is done cooling. I can pull this off, close this piece away. Send this off to the side, as well as pull this clamp off. And this piece of wood. So now you can see we have this piece of plastic at a nice 90-degree angle.
Site on the end of the PowerPoint if you ever want to see it again. Keeping screwed and set screws in place. So the last thing you want to happen is a mechanical failure happen because of something as simple as a screw or set screw falling out. And there's some ways you can do to prevent this, such as putting nylon nuts on the end of bolts to keep them from sliding off, and also adding Loctite into the crevices to keep the set screws in place.
What are those screws that come with your Tetris kit? How many kept nuts do you guys have on your robot?
Zero. And if we had any, they'd probably be off by the time we made it into a tournament anyway.
The problem with kept nuts is they have these little teeth, basically, that hold them in place. But because while your robot is moving, it's vibrating a lot, and there's a lot of shocks into another robot. And what usually happens is those will loosen, and after a couple rounds, they'll fall off. Your robot, the sign of your robot. We always use nylon.
And then not transmitting load through axles. And we'll explain this more on the next slide. And then this is a kind of a counterintuitive principle, but friction doesn't depend on surface area. So if you have the size or the size of the object, such as if you have more wheels, it doesn't mean you have more friction or traction. Because the bigger the surface area, all the force is being dissipated in a more even area. So like it's more spread out basically. So just because you have more wheels or bigger wheels doesn't mean you have more friction. And finally, compression components under tension and compression. So understanding the principles of how metal works. For example, there's a soda can challenge. You can try to stand on a soda can, and if and the ground is perfectly flat, the soda can will actually support your whole weight. This is because metal is much stronger under tension and compression as opposed to flexing. So understanding these principles can help you make something really light and strong.
Okay, so number one, who was best at this? Was it Sean? Sean, let's see if you can do it. So it's a soda pop can. As long as the metal is under compression, it'll support his weight. Now, I'd like Nathan to get down there to touch the side of the can. As soon as it came out of straight compression loading and became a flex load, came out of column, boom, strength is gone.
So this goes along with the principle of not transmitting a load through the axle. So here we have a sprocket attached to the wheel and 4 screws going through that. So instead of having the load being transmitted through a thin axle, it actually spread out through all 4 of the screws, and so through that it becomes a shearing force on the 4 screws instead of a load going through the axle.
Tools and using them. So we color code all our tools. Roy did, so red is bigger than violet. Orange is what we use for normal socket heads. Yellow is for motor, axle hubs, motor and axle hubs. Green is for our button heads, and then blue is for the old style axle shaft colors. And good mechanics have their own tools. We all have our own set of tools that we'll take with us to like a tournament. That way, if we want to go help a team or we need to go do something somewhere else, we can take those tools with us. And then the team has their own tools that they can use. We're never taking tools away from the team that they need. Removing cross-threaded machine screws and removing rounded out machine screws, basically trying to get a bigger lever That way you can get more force on it. The one way to do this is by using vice grips, just clamping onto the head or whatever's left and twisting. Also with cross-threaded machine screws, you can just try drilling them out. And then for removing roundabout machine screws, there are special bits called easy outs. And how it works is you like drill into it, and then when you reverse the drill and go the other way, the teeth, it has like burrs in them, and it'll pull it out and unscrew it.
Calculating loads on lever arms. So this is an important thing to do. It's something that we'll do if, say, we're ever creating an arm like on this year's robot. We always try to go through and calculate how much weight we think we'll need to lift by the end of the arm to see how much we need to gear it or how many motors we need to put on that arm. So we always have a margin of safety of at least 2 to 1. So we know the theoretical stall current and outs inches of torque that a DC motor will put out that I'll actually show on a slide a little past this. But we always try to have a margin of safety of at least 2 to 1, as in we always should have twice as much power as we're calculating. So one thing you can do at home that's kind of fun to do, just a little test, is you can make an arm with a DC motor, at least 1 gear change, and a lever arm on the end. And try to see how much weight your lever arm can pick up, theoretically, at the end of the arm. So this is a good example of a lever arm that's on our robot over here from 3 years ago. And you can see the arm is this piece of channel here, and you have a cascading gear system that actually put it in a 9 to 1. And then a DC motor you can sort of see coming out here. But before we actually designed it or implemented it, we tested before how much weight. We took the weight of a basket that it would need to pick up to see how long it could be, how strong or what gear ratio we really needed to pick up the basket. And then this is the motor power table that we go off of. We sort of compiled it off of a lot of the motors that we're allowed to use in FPC. I think this is on our website in a couple different places, and we'll be putting the slideshow on the website as well. So if you guys ever need to reference this, it's up there.